All right, again, welcome back to Calc 1 Honors. Today is going to be another fun day of integral calculus. If we're lucky, we might even see our first integral, which is always a wonderful big step. So let's get into it. Stuff out of the way. You guys don't need any of that. All right, here we go. I want to say I appreciate very much the work that you guys have been putting into your honors projects. A few of you have sent me several drafts and they're coming along beautifully. If you haven't shared a draft with me yet, I want to strongly encourage you to do that. So we don't want the end of the semester to come around without you having gotten any feedback from me on your honors project. It is definitely a sizable chunk of the grade, and it's something that you really want to make sure is up to par. And I know that the guidelines for the honors project are very vague, so it can be quite nerve-wracking. And while I do grade them gently, there are also, some standards. I do want to see that you've put in some work and done some research and come up with some conclusions. So make sure you're sharing a draft with me. Everybody who has done so far is doing wonderful work, and that's great. But there are a few of you I haven't heard from yet. So I would like, in your own time, of course, not something to panic or rush through, but make sure that you have a draft. If you're still working from an outline, that's okay too. Maybe just share the outline with me. Just let me know where you're at so we can talk a little bit. But we do want to be moving from the outline stage into a draft by this time. And I just wanted to let you know that I'm more than happy to look over drafts with you, and I would really appreciate it. All right, today we're going to say, I think we finished 5.1. Is there? Yeah, so we're going to begin 5.2. Which is on the definite integral. So the good news is we're leaving Riemann sums behind. We're almost to a place where you won't need to mess around with Riemann sums at all anymore. And that's a nice thing because I know nobody likes Riemann sums. They're clunky. There's a lot of drawing, writing, calculating, stuff that is just not especially pleasant to do by hand. A very smart man once told me that the kind of good litmus test to see if you will enjoy being a mathematician is if you're willing to work very, very hard so that one day you might be very, very lazy. Mathematicians love to prove theorems, which is incredibly hard to do, so that in the future they can just cite that theorem and say, this is something we've done before. All right. The work of proving the theorem is non-trivial, but once you have it, it's like a whole universe of problems are resolved at once. It's a beautiful thing. And the more general the theorem, the larger the class of problems that are resolved by it, sort of the more satisfying the proof of the theorem feels. 5.2 is really about notation, more than it is about a theorem. 5.3 is about the theorem, which will connect the notation that we're going to introduce today with the Riemann sums that we were computing in the last two classes. That theorem is called the fundamental theorem of calculus. And when you hear the word theorem, you know, okay, this is going to be fairly general, fairly important. When you hear the word fundamental theorem, that kind of screams massive generality. So the other place you may have heard those words next to each other is in your pre-calculus class when you learned about the fundamental theorem of algebra, which says that all polynomials can be factored and the factors always correspond to roots, and that if you have a polynomial of degree n and you count the roots with multiplicity, then you always have exactly n factors. It's like this beautiful deep connection between the expanded form of any polynomial and the factored form of any polynomial. And it brings together a bunch of things from analysis, complex analysis, and algebra. So it's a truly beautiful thing. The theorem that we're building up to is the fundamental theorem of calculus, which does something similar in that it connects the tangent line problem, the derivative, with the area problem and the integral and something called an antiderivative, all in one little ball, which is quite amazing. But the notation that's used to express the fundamental theorem is the definite integral. So the kind of two things we need to talk about before we can dig into 5.3 are definite integrals and antiderivatives. So we're also going to discuss antiderivatives, which I think is section 4.9. So it's kind of a step back, but it makes more sense to do it here because this is where we're going to start using it. Let me pop open your textbook. I want to go through the theorems in order and make sure that everything's presented in as logical a fashion as we can. So we're going to begin with the definition. I'm going to try to make this as tractable as possible. So how do I say this? If f is a piecewise continuous function on the interval closed bounded interval AB, then the definite integral from x equals a to x equals b of f is defined by, so here's the notation. It's a big, long Latin letter S, right? The Latin alphabet is the alphabet I'm writing in here. Yeah, just the regular English alphabet, if you like, same as the Latin alphabet. So it's the same as this letter, S. It's just stretched out. And the reason we use the letter S is because it represents a sum. Just like capital sigma represents a sum, we use the Greek letter S there. Here, that's like a blocky S, and it is kind of a blocky sum in the sense that it's a sum over discrete values of n. Here, this is kind of a smooth, curvy S because it's kind of a smooth, curvy sum. You can think of this as the sum of all the values, all the outputs from the function f over the interval AB. And we write it as integral. This is called the integral symbol from a to b of f of x dx. The dx at the end here is kind of like the delta x in your Riemann sum. If it were up to me, I would probably just write it as integral a to b f of x at this stage. But the standard notation and interesting connections to differentials that we talked about back in section 3.10 and differential geometry obligate us to write the integrand as f of x dx. This is defined to be, right? So that's the notation. And by definition, this is the limit as n goes to infinity of, I'll just say Rn, or the limit as n goes to infinity of Ln, or the limit as n goes to infinity of Tn. You could take any of those approximation schemes, including the midpoint scheme or the other one we talked about, Simpson's rule, and take the limit as the number of rectangles goes to infinity in all of those. And that is the thing we call the definite integral. Oh, Talia reminds me that 4.9 is one of hers. Let me see. So
is it a Tn is midpoint?
Tn is the trapezoidal rule. So let me see. Really quick here.
I don't remember what is that.
We can take a look back at the previous lecture where we discussed Tn. Tn is the average of Ln and Rn. It's 1/2 times Ln plus Rn. Here, 4.9 antiderivatives. Yeah, Talia, that's you. All right, so I won't dig into that, but we do need to talk to you because we are getting quite close to that. So we're just going to talk about the definite integral today. I'll discuss this, but we won't cover the subject in its entirety. We can do 4.9 anytime around 5.3, but we will need to discuss antiderivatives in order to introduce 5.3. Okay. So what is this thing? You can just think of it. I encourage you to just think of it like this. Because every time we did an exact area calculation, we just used the right endpoint Riemann sums. And this is where Rn is sigma I from 1 to n f of xi times delta x, with delta x as b minus a over n and xi as a plus I delta x. So this thing, the definite integral, is the limit of the Riemann sums. And we've seen previously that this is the exact area bounded by a positive function f of x from a to b. What this means is that the integral here, let me discuss first some terminology. The thing inside the integral f of x is called the integrand. The thing you're integrating is called the integrand. The dx at the end is called, we talked about these before, the differential. And the symbol is called the integral symbol. All right, and it turns out there are going to be two types of integrals, the definite integral, which we're discussing today, and the indefinite integral, which is intimately connected to the thing Talia is talking about, the antiderivatives. For us, we should think of, so intuitively, integral a to b of f of x dx should be thought of as the signed area, I should say the exact signed area bounded by the graph y equals f of x and the x-axis from x equals a to x equals b. This is the way everybody thinks about these things. So we know that the limit as n goes to infinity of Rn returns the exact area underneath the curve y equals f of x. All of the examples we've looked at where we calculated an exact area using a limit of a Riemann sum, that function was positive, right? So all the area lived above the x-axis. What I mean by signed area is that if some of that area is below the x-axis, it will be counted as negative. And if the area is above the x-axis, it will be counted as positive. So this is this is what we mean by the definite integral from a to b of f of x. It is the exact signed area bounded by the curve over the interval ab. And there are some problems where you're asked to express a definite integral as a limit of a Riemann sum, or vice versa. Given a limit of a Riemann sum, write it as a definite integral, and that's just notation. The fun stuff here is some properties of the definite integral that come from this geometric definition, or this geometric intuition. A couple other things to discuss. You'll notice I've said f should be piecewise continuous. What I mean by that is that f doesn't need to be continuous, but it needs to be made up of continuous parts. So you can have a jump discontinuity as long as the two pieces on either side of the jump are themselves continuous. You can't have vertical asymptotes. That's not okay. That kind of discontinuity does not yield a piecewise continuous function. So as long as f can be thought of as multiple pieces, each of which is continuous, then the definite integral is well defined. But if you have things like vertical asymptotes, or a function which cannot be thought of as like separate chunks that are continuous, like that Dirichlet function, the definite integral is not well defined for those. The cool thing is that the other kind of integral that we talked about, the Lebesgue integral, is well defined for those. But you'll need to take a graduate course if you want to discuss Lebesgue integration. That's a little bit trickier. So the particular kind of integral we're talking about here as a limit of a Riemann sum is called a Riemann integral. This is a definite Riemann integral. And everywhere in your undergraduate calculus, you'll be working with Riemann integrals. Okay, so they give you a slightly more general looking definition here, where instead of talking about left endpoints, right endpoints, midpoints, trapezoid rule, whatever, they're just saying let these be any sample points. Then the definite integral will be the limit of the Riemann sum associated with those sample points. If this limit exists, we call the function integrable. So in place of the word integrable here, I'm using piecewise continuous, because if your function is piecewise continuous, then this limit will exist. If your function is not piecewise continuous, then this limit will not exist. They're almost exactly the same. There are some slight variations on this depending on what sample scheme you're using, but for us, piecewise continuous is equivalent to integrable. I guess other terminology, let me make sure I'm not leaving anything off. So yeah, the thing inside is the integrand, the thing at the end is the differential, the S is called the integral symbol, and the numbers a and b are called the limits or bounds of integration. Let me squeeze this in here. The numbers a and b are limits or bounds of integration. So those are words that I'll be using pretty freely. I'll refer to a and b as the limits or the bounds. I'll refer to the inside as the integrand, and dx or dt or whatever as the differential.
Wait, sorry, which one's the integrand?
The integrand is the function inside, the thing being integrated.
Ah, cool, thanks.
Yeah. All right. Some definite integrals are very easy to calculate using geometry. So I could say calculate the integral from 0 to 2 of, let's say, 3x dx, and calculate the integral from -2 to 2 of the square root of 4 minus x squared dx using geometry. Or by interpreting as areas. I'm going to give us one more here too. How about the integral from -1 to 3 of x dx? We'll start with these.
Is the first, oh, sorry,
Oh, it's okay. What's up?
I thought the first one had the same bounds as the second one.
Oh, no, I'm just making stuff up here.
Cool. No, if it did, it would be 0.
Yeah, if this was from -2 to 2, that would be 0. That is true. So let's do it. I claim that if we think of each one of these objects as an area, then we can use formulas from geometry to find the value of each integral, because each integral represents an area. So for part A, all of these, I'm going to look at a graph. I'm going to look first at the graph here, y equals 3x. We know what that is. That's a line with slope 3 going through the origin. It looks something like this. And I'll mark this as 1 and 2. This point here would be 1, 3. This point here would be 2, 6. And the integral in question is measuring the signed area bounded by this curve from 0 to 2. So this area is the integral from 0 to 2 of 3x dx. But also, area is a triangle. The area of a triangle. So that's going to be 1/2 the base times the height. Right? That's how you find the area of any triangle. So what is the base of this triangle? Well, it's 2. What is the height of this triangle? Well, that's 6. So this is 1/2 times 2 times 6. Yeah, which is, Sarah said in the chat, is 6. So the integral from 0 to 2 of 3x dx, that's 6. No calculus at all. Right? We didn't have to do any differentiation or limits or anything like that to find this area. And kind of nicely, no Riemann sums either, right? Part B, we might need to think about a little bit more carefully. So I am going to cover the solution to A here in just a second. Are there any questions on what we did to find the integral in part A? I see something else in the chat. Yeah, B, we're going to get there by thinking of this as a semicircle. Now, I'll tell you, throughout this course and the remaining weeks, we are going to develop lots of tools for evaluating integrals. But this integral is going to escape our calculus tools until about the 3rd or 4th week of Calc 2. Actually finding this guy using the kind of standard calculus tricks is very hard. It requires something called trig sub. But if I begin by thinking about the graph y equals the square root of 4 minus x squared, I can square both sides. So I want to know, what is this curve, right? I want to draw the graph. And to that end, I'm going to square both sides. It becomes y squared equals 4 minus x squared. And then adding x squared to both sides, this is x squared plus y squared equals 4. And like Sarah said, that's a circle. It's a circle of radius 2 centered at the origin. So x squared plus y squared equals 4 is the whole circle. The positive square root is just the upper semicircle. So I'm going to come in here and point out the difference. This is y equals the square root of 4 minus x squared. So the whole circle is both the positive and negative square root, the upper and lower semicircle. So here, the area I'm calculating is the area from -2 to +2 under the blue curve, which is this area. So this area, this is 1/2 the area of the circle. Right, the full circle is not what I'm looking at because this is just the positive square root. If you like, I can illustrate down here. Oh, that's awfully close in color, isn't it? I'm sorry, I don't have many other colors available right now. This piece down here would be y equals the negative square root of 4 minus x squared, and that's not what I'm dealing with. So the area I want is just the area bounded by the upper semicircle from -2 to 2. That's 1/2 pi times the radius squared, because the area of a circle is pi r squared. The radius of this circle is 2. So this is 1/2 times pi times 2 squared, which is 1/2 times 4 pi, or just 2 pi. So the integral from -2 to 2 of the square root of 4 minus x squared dx is indeed 2 pi. Is everybody comfortable with the graph of the circle, the upper semicircle, lower semicircle stuff? Kind of, if you take this equation, which is the equation for the whole circle, and try to solve it for y, you would get y equals plus or minus this square root. The positive version is the upper semicircle, which is the curve we were given. The negative version is the lower semicircle, which doesn't have anything to do with what we were given. So he doesn't factor into this at all.
Is if the lower semicircle, it should be y is equal to minus square root 4 minus x
That's correct.
2 degree. Okay.
Yep. Yeah, that's exactly right. Okay. Neither of these were too bad. Let's look at this last one. So I'll just copy it down here so we don't waste too much paper. See here, we want to define the integral from, what did I say, -1 to 3? Yeah, -1 to 3 of x dx. So the curve we're looking at is nothing fancy. It's y equals x. But here we're going to have to think about that signed area thing. I'll continue this over a little bit further. Yeah. So this region whose area is being measured, or this curve whose area bounded from -1 to 3, some of it's below the x-axis, some of it's above the x-axis. And because the integral measures area with the sign, we need to be careful to make sure we measure this area as negative and this area as positive. So here's what I'll do. I'll label this as A1, and I'll label this as A2. And what's true here is that the integral from -1 to 3 of x dx is negative a1, because the area from this a1 region is below the x-axis, plus a2, because that area is above the x-axis. So this is what I mean by signed area. Because this guy is below the x-axis. We count that area as negative. The y values there are negative. Now the rest of it can be done the same way, right? The height here, this is the curve y equals x, so this is the point 3, 3. This is the point -1, -1. Sorry, that doesn't show up there, does it? This is the point -1, -1. So a1, I've got my negative out front. The base times the height here are both 1. Plus a2. Oh, sorry, I need a 1/2 also. So negative, right? 1/2 base times height. A2 is 1/2 his base times his height, which are both 3. So this is -1/2 plus 9/2, which would be 8/2 or 4. So kind of the area down beneath the x-axis cancels some of the area up here above the x-axis. Are we all comfortable with this idea? Are there any questions about why we're measuring a1 as negative and a2 as positive? Okay. Some fun properties of the definite integral can be illustrated using the geometry. So what I'm going to do now is discuss just a couple properties. We will more than once visit this topic of properties of the definite integral, but I'm going to start with the ones that are the easiest to see just through pictures. So I have some curve here, y equals f of x. And I have some interval from a to b. And I'm going to assume that between them is some number c. The total area being measured here. So where are you? Total area being measured here is all of this stuff, right? But I can think of it as coming from a sum of two areas. So the total area total pencil shaded area this would be all the area bounded by the curve y equals f of x from a to b. That's the integral from a to b of f of x dx. But if you look at just this first region here from a to c, that's the integral from a to c of f of x dx. And the second region would be the integral from c to b of f of x dx. So what's the conclusion? Well, certainly, if I put these two little areas together, I get the total area. The total area is the integral from a to b, and each of the little ones is integral a to c plus integral c to b. So the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. And this is actually a theorem. We'll just call it a property. It's not something that requires any sort of advanced proof. It's evident from the picture. And this is a very useful property. You can split up an integral. There are many ways you can split up an integral, but this is one of the simplest. You can split it up over the bounds, over the limits. So if you're going to try to integrate from a to b, but maybe it's easier to do this one on its own, and it's easier to do this one on its own because of some feature of the geometry, then you can do that. You can do the integral from a to c on its own and add that to the integral from c to b, and that will give you the integral from a to b. So this, very useful fact.
Excuse me, but f of x, is it linked to the same equation?
Yes, same function, must be the same function. Right, because each of these little areas, they're coming from the same curve. Now, if you had a piecewise function where you've got one equation defining f here and another equation defining f here, that would be one of those examples where it's easier to do them separately. But the idea is it's coming from the same graph. We have to be able to think of it as a single graph. Before we dig into other properties, let me just find an example problem here that is useful like this. Continuous functions are integrable, evaluating integrals. We've done plenty of this Riemann sum limit shit. I don't want to beat you up on that. Let's find, no, we're gonna do that later. We'll do that later. We need an example problem here. There might not, there it is. That's boring. Something, come on, something. Maybe I'll just juice one up for us on our own. Yeah, all right, let's do it like this. So suppose the integral from 0 to 1 of f of x dx is equal to -12, and the integral from 1 to 3 of f of x dx is equal to 21. Find integral from 0 to 3 of f of x dx. I know this might seem a little bit silly, but the idea is that f is just one particular function here. So the integral from 0 to 3 is the integral from 0 to 1 plus the integral from 1 to 3. So I'd say, all right, that is integral 0 to 1 of f of x dx plus the integral from 1 to 3 of f of x dx. The integral from 0 to 1 of f of x dx, I was told, is -12. And the integral from 1 to 3 of f of x, I was told, is +21. So all together, I get the integral from 0 to 3, and that has to be 21 minus 12, which is 9. Sorry, there we go. Oh, very good. The next property I want to discuss with you is another one that comes straight from the picture. And this has to do with even and odd functions. If f is an even function, or at least behaves like an even function on negative a to a, well, I should say an even function continuous on negative a to a, then the integral from negative a to a of f of x dx, let's think about the graph. So maybe negative a is over here, positive a is over here, something like this. So the total area being measured from negative a to a would be all of this. And due to the symmetry of the graph, the total pencil shaded area is double the blue area, right? The area bounded over here is the same as the area bounded over here. So the total area is double this area. In other words, the integral from negative a to a is twice the integral from 0 to a. This can be time saving, right? Rather than having to calculate all of it, calculate the part from 0 to a and then just double that. You could also calculate the part from negative a to 0 and double that. Same thing. It's especially useful later once we have the fundamental theorem of calculus, because the way we evaluate these integrals using calculus is by plugging numbers into something called an antiderivative. And 0 is always a nice number to plug in. There's another version of this that's even nicer. If f is an odd function continuous on the interval negative a to a, then the integral from negative a to a of f of x dx. Again, before I write down the answer, let's look at the picture. Talia brings up an interesting question. So we don't have to worry about things over here being negative. It's true. Remember, it's not the x values being negative that can give us negative areas. It's the y values being negative. And while I drew this graph so that all the y values are positive and hence all the areas would be measured as positive, even if some of the area over here was negative, there would be a symmetric piece of negative area over here. So this works whether f is a positive function or not. This actually works in general. It's just easier to picture if all the area is positive, so I drew it that way. But here we'll be thinking about negativity because odd functions don't have y-axis symmetry, they have origin symmetry. So if I draw a function that is symmetric about the origin, something
Do
like
they end up just equaling 0 in that case?
it will, yeah. So if I put negative a over there and positive a over here, and again, the area being measured, let's take a look. Remember, we're measuring signed area bounded by the curve. So this chunk would be measured as positive. But by the graph symmetry, this chunk over here, which would be measured as negative, has to be the exact same size. So this positive piece will be perfectly canceled by this negative piece. And this positive piece will be perfectly canceled by this negative piece. Which means, yeah, the integral from negative a to a of a continuous odd function is always going to be 0. And talk about a time saver. One of my favorite examples, and I put this on exam 1 in my Calc 2 class once, they really didn't like it, was to compute, oh, my wife is calling me, I'm so sorry, I have to answer this. Hey baby, what's up?
Hey, what's your PIN number to your card? Because they're asking, because I need to withdraw money from the card because you're not here.
My debit card?
No, your bank card, your credit card.
That shouldn't have a PIN, but the PIN to my debit, which is the only one I've ever said, is 1326. All right, I gotta run. I'm teaching.
Okay, bye.
All right, sorry about that. So, fun example here. I had my Calc 2 students evaluate the integral from -1 to 1 of the inverse tangent function. And if you do this sort of the standard way, it involves something called integration by parts, which is a little bit messy and requires you to remember things like the derivative of the inverse tangent function. This is, I'm sorry, guys. Sorry about this, guys. My wife is at the DMV right now trying to replace her ID, and they won't let her run my credit card because I'm not there. So she's trying to pull cash out of the credit card, but of course that's not how credit cards work. So I need to Venmo her really quickly. Anybody want to tell me what the integral from -1 to 1 of the inverse tangent function is?
0, because it's tangent on its side, so it's going to be exactly split negative to positive over the origin.
Yeah, exactly. Charge fees. I know this sucks. Go ahead. All right. Yeah, the inverse tangent function is an odd function. So the integral from negative anywhere to anywhere of the inverse tangent function is automatically 0. And you can imagine if you've spent the last few weeks grinding out techniques for integration as a Calc 2 student, you might just want to dive into that using those techniques instead of thinking, oh, hang on. This is an odd function. So the negative area over here from -1 to 0 is exactly the same as the positive area over here from 0 to 1. So I'd say, because Oh my God, she needs to stop calling me. Yes, sweetie, I'm teaching. What's up?
With taxes and everything, it's going to be like another $6.
How much do you need altogether?
36.
All right, baby, I'll send it.
Thank you.
All right, I gotta go. This is 0. This is ridiculous. All right. So sorry about this, guys.
Excuse me, I still cannot understand why it's the 0.
So it's a consequence of the property that we've listed up here. If you integrate any odd function, which is continuous, over an interval that is symmetric about the origin, you will always get 0. The reason is that this area is the same as this area. A1 equals A2, but the integral -1 to 0 of the inverse tangent function, that would be -A1, and integral 0 to 1 of the inverse tangent function, that would be +A2. So the integral from -1 to 1 of the inverse tangent function is -A1 plus A2. But because A1 and A2 are equal to each other, when you add these up, you get 0. So imagine this area is like 3. Then this area is also 3. But because this area is beneath the x-axis, the integral will measure it as -3. And this being above the x-axis means it will be measured as +3. So -3 plus +3 is 0. And it works the same for any odd function. There's exactly the same amount of area beneath the x-axis as there is above the x-axis. So when you add them up, the stuff beneath being counted as negative and the stuff above being counted as positive, they'll always cancel perfectly and give you 0.
So if for the even function, they will double error, but if for the odd function, the error always 0.
Correct. An even function, you've got the area matching up perfectly and with the same sign. With an odd function, you've got the areas matching up perfectly, but with opposite signs. So when you add things of the same size, but opposite signs, we always get 0. And when you add things of the same size with the same sign, you get the double of either one. And that's the idea. There was another question here. How can you tell if a function has symmetry? How can you tell whether a function is odd or even? That's a subtle question. The sloppy answer to that question is look at the graph. Right? If the graph has y-axis symmetry, then that's an even function. If the graph has origin symmetry, that's an odd function. But there are some tricks to recognizing even and odd functions. So I can share with you a few quick facts. A polynomial, so even and odd functions. Any polynomial with only even or odd terms will be even or odd. So I'm writing two statements at once here. If you have a polynomial where all the powers are even odd powered terms, then that's an even function. If you have a polynomial where all the powers are odd, that's automatically an odd function. And this is kind of where the terms come from. The reason we call them even and odd functions is because of this fact. Sine, tangent, and cosecant are all odd. Cosine, let's see, is cotangent even? No, I should add, sorry, so is cotangent. Cosine and secant are even. So from your trig functions, not leaving anybody else, 1, 2, 3, 4, 1, 2, no, that's all of them. In general, it's also true that the hyperbolic sine and hyperbolic tangent are odd. Hyperbolic cosine and hyperbolic secant are even. In general, an odd function is one which satisfies the functional equation f of negative x equals negative f of x. And an even function, these are actually the definition, is one which satisfies f of negative x is equal to f of x. There's more that could be said here, but I don't want to spend too much time on this because it's not really a calculus topic. This is definitely something from pre-calc, but it doesn't hurt to revisit it. So easiest ones to recognize: polynomials. If all the powers are odd, that's an odd function. If all the powers are even, that's an even function. If you have a mixture of even and odd powers, it's neither. Your trig functions, sine, tangent, cosecant, and cotangent are all odd functions. Cosine and secant are even functions. And
excuse me, you said that the power, is it the largest power, the biggest power is if it's a polynomial and the largest power is equal to 4, so that is a even function. But if
let me hold just for a second there. So it's not the largest power. It has to be all of the powers. So let me flip over to Desmos here. I think some examples will help. For polynomials, if I take something like x to the 6, let's do 6 minus 2x to the 4 plus x squared minus 1. This is an even function, right? Its graph has y-axis symmetry. If I take something like 4x to the 5 minus 2x cubed plus x, change to minus x, yeah. The blue is an odd function. He has origin symmetry. So if all the powers are odd, that will be an odd function. And if all the powers are even, that will be an even function. But if you have a mixture of powers, like 2x to the 4 minus x cubed plus 4x squared plus 2x minus 1 or something, you're going to get neither, right? This doesn't exhibit either of those symmetries. So for polynomials, you need all the powers to be odd, that'll give you an odd function, or all the powers to be even, that'll give you an even function. And constants are even powers, that's x to the 0. So like if you take this guy and you add a constant like plus 5, no longer an odd function. So if all the powers, if you have only even powers, then that will be an even function. If you have only odd powers, that will be an odd function. Trig functions, sine, tan, cosecant, and cotangent are odd. Cosine and secant are even. Same is true for the hyperbolic trig functions, sine, hyperbolic, tangent, hyperbolic. Indeed, cosecant and cotangent hyperbolic would also be odd. Cosine hyperbolic and secant hyperbolic are even. And these are your general definitions. There are other rules, like an odd function times an odd function is an even function. What else? An even function times an odd function is an odd function. You can explore those things in your own time. But what we're trying to do here is just wrap our heads around how the graph symmetry relates to these facts about integrals. Before we spend too much more time on this, there are a couple other properties that I want to share with you that aren't quite as obvious from the picture. So before we wander away and get lost in even and odd functions, as cool as they are and as much as I love them, we do need to talk about one or two other properties here. All right. These other guys are considerably less obvious. And the way we usually think of them is as a consequence of the Riemann sum. So here I won't be able to draw a picture for you that totally explains it, but let me share this. So the integral from a to b of f of x dx is the same as the negative version of the integral from b to a of f of x dx. This comes from looking at the delta x term in the Riemann sum. Delta x here is b minus a over n. Delta x here in your Riemann sum would be a minus b over n, which is the negative of b minus a over n. So because the delta x's in the Riemann sums are negatives of each other and everything else is the same, these integrals are opposite signed. In other words, if you flip the bounds over, if you exchange the limits of integration, a negative pops out. The other two rules here are linearity rules, and these again come from the Riemann sum. So if you have an integral where inside you have f of x plus g of x dx, this is the same as the sum of the integrals a to b f of x dx plus integral a to b g of x dx. And if you change the plus to a minus, you change this plus to a minus. The last one here, integral a to b of a constant k times f of x dx is the same as that constant k times the integral from a to b of f of x dx. And these two, so we've discussed linearity a few times with the derivative, which is a linear operator, the sigma, which is a linear operator. This means that the definite integral is a linear operator. And again, linear operators, as we said, with derivatives and sigmas, are the only kind of operators that we really want to mess with. They are everybody's favorite operators. This is a consequence of a field of mathematics called linear algebra, which says we can do all sorts of nice stuff with linear operators that we can't do with nonlinear operators. Before I let you go, I do want to work a few problems exhibiting these. I also want to convince you that this is true, because I feel like none of these are obvious. These do not come from the picture, or at least not so cleanly from the picture. So a quick idea of the proof. For one, the integral a to b f of x dx is the limit as n goes to infinity of Rn which is the limit as n goes to infinity of sigma I from 1 to n, f of xi times delta x, which is lim n to infinity, sigma I from 1 to n, f of xi times b minus a over n, because delta x is b minus a over n for that integral, which equals dot, 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 equals then n to infinity, sigma I from 1 to n, f of xi times negative b minus a over n. Sorry, a minus b. Shit. So if you factor a negative out from this b minus a, that changes the order of subtraction, right? Try redistributing this negative. This is an a, this is a b. When you distribute this negative, you get negative a plus b, which is b minus a. But now I can bring that negative out front. This is lim n to infinity, negative sigma I equals 1 to n, f of xi a minus b over n. Here I'm using the linearity of the sigma operator, which says constants can pop out of it. And that negative 1 is a constant multiple, so it can pop out of the limit or pop out of the sigma. And then because of the linearity of the limit operator, this is negative lim n to infinity, sigma I from 1 to n, f of xi times a minus b over n, which is exactly negative integral b to a, f of x dx. So it is true, as a consequence of the definition and just the algebra of the Riemann sum, the integral from a to b is negative the integral from b to a. If you flip over the bounds, a negative pops out. 2 and 3 I can prove together by looking at the integral from a to b of f of x plus k times g of x dx. And I will show that this is the integral of f plus k times the integral of g. And that proves 2 and 3 simultaneously. This would be the limit as n goes to infinity, sigma I from 1 to n, f of xi plus k times g
You
of,
move the dot cam up slightly.
oh, sure. G
Thank
of
you.
xi times delta x. And I'm not going to write out what the delta x is here because it doesn't factor into this the way it does in the previous one. So here is the limit as n goes to infinity of Rn for this integral. And then using the linearity of the sigma, I can split this up. This is lim n to infinity. I'm going to split up that sum as sigma I from 1 to n, f of xi times delta x plus k times sigma I from 1 to n, g of xi delta x. And then sort of distributing that limit using our limit laws or the linearity of the limit operator, we get lim n to infinity, sigma I from 1 to n, f of xi times delta x plus k times the limit as n goes to infinity, sigma I from 1 to n, g of xi times delta x. And each of these are Riemann sums for a certain integral. The first one is the integral from a to b of f of x dx. This plus is this plus, this constant k is this constant k, and this piece is the integral from a to b g of x dx. And that's the proof. In some sense, these properties 2 and 3, the linearity of the integral is by far the most important. It says that you can take an integral or area problem for a big complicated function and split it up and find the area or integral for each of the little pieces, which is very, very nice. In the same way that you can split up derivatives, right? If you can write your function as a sum or difference of other functions, then you can just take the derivative of each one on its own. This says if you're trying to integrate a sum or difference of functions, you can split it up and integrate each one on its own. And that's a very nice thing to do. I think this is probably a good place to hold off. Let me make sure I'm not missing any theorems from this section. I believe we've hit everything. Oh, the comparison stuff. Yeah, all right, that's going to have to wait. This is going to take a little bit of time to explain. So next time we will talk about comparison properties. Yep, and then we'll be done. This one of the other properties that's in here, the integral from a to a being 0, is actually a consequence of the comparison property. So next time, next time we will talk about the remaining properties of the definite integral. But this guy and linearity, which they write as 3 separate things, are all pretty natural. This one I wouldn't even consider a property. This is literally just the area of a rectangle, and this will come from the comparison property. So I'll leave it here for now. And on Friday, we will talk a little bit more about properties of definite integrals, and also we will work out a bunch of examples to make sure you're nice and comfortable for the homework. Talia, if you could come meet with me, please, that would be good, because we do need to get the antiderivative stuff sorted out before we can move into 5.3. So I think probably you're coming up Monday, maybe. That's a little bit rushed. So let's please make sure we talk either today or Friday in office hours and get everything squared away. And besides that, I've got nothing else for you guys today. I hope you have a good rest of your day. And if you need anything from me, you know how to reach out. Canvas messages, Discord, office hours, all of those things. Take care again.
Also,
Thank you.
Professor Faustigan?
Yes.
I can't come to today's office hours, and I would only be able to come to like 15 minutes of Friday's office hours. Would there be any way I can meet with you tomorrow?
Yeah, are you available tomorrow morning at like 10?
Yeah, for sure.
Okay, while I have you here, let me go grab a Zoom link for you, and we can have
Awesome,
a
thank you.
meeting tomorrow at 10.
Yeah, that'd be great.
All right, here we go. So that's going to be the 11th at 10 o'clock a.m.
Professor John, I sent an email to you. It's about the statistic in the project.
Okay. I will take a look at that. I have a handful of emails that I've not yet been able to get to, but I should be able to clear that out this afternoon. So I should be able to email you back either later today or early tomorrow morning.
Thank you.
Alrighty, and Talia, if you look in the chat here, I'm going to send you a link. If you save that link just somewhere in like Notepad or something like that, that's where we will meet tomorrow, okay?
Yeah, awesome, thank you.
Alrighty. Just let me know when you got it saved. I'll hold the meeting open until we're done with that.
Okay, I have it.
Alrighty then. I'll see you guys next time.
All right, thank you.